Hello guys, welcome back to another video. In this lesson, we are going to cover Charles's Law and Boyle's Law. We left off our last lesson talking about the different gas laws. In this video, as I mentioned, we will focus on calculations. We left off our last lesson thinking about the three equations, or without counting, of course, Avogadro's one. The three equations that we learned, is there a way to combine them? I wanted to see the variables that show up on the top of the fraction and the ones that show up on the bottom. So if we kind of put them all together, they blend in to the combined gas law. Now in this lesson, we are not going to go over this, the combined gas law just yet. There will be a different lesson for that. However, it is important that we look at it beforehand because as we start talking about Charles's Law and Boyle's Law, I want you to see that the relationship between the two is going to be slightly different. For example, we know that Charles's Law is going to involve volume and temperature. So we can ignore pressure and we would end up with the equation for Charles's Law. However, if we were to ignore instead the temperature, we would end up with Boyle's Law. So that is where the combined gas law comes into play. And really, you only need this one equation to figure out the other three gas laws. So with that in mind, let's go ahead and do a quick recap on Charles's Law. We said that Charles's Law involves temperature and volume. The higher the temperature, the higher the average kinetic energy of the particles of the gas, the more they will expand out. So they're going to have more space in between each of those particles. So they're going to take up more volume. Therefore, we say that it's a direct relationship. Here, of course, we are assuming that our constants are, so meaning they don't change, it stays the same, the number of moles and the pressure. So here on top, we have V1 over T1 equals to V2 over T2. So we are going to look at two examples. Let's look at Charles's Law first example. A couple of things that we need to take into consideration before we begin with the actual calculation. Every time that you have temperature, you must change your degrees Celsius into Kelvin. Remember, in a previous lesson, we talked about that. In order to get kelvins, we are going to do the degrees Celsius that are given, and we're going to add the constant 273. So here in this example, just by glancing at it, before we even read it, I can see that there's 25 degrees Celsius. So I know that at some point, I'm going to have to change that into Kelvin. So let's go ahead and read the question. It says, what is the temperature of a gas that is expanded from 2.5 liters at 25 degrees Celsius to 4.1 liters at constant pressure? Now here this problem is telling us that it's constant pressure, but it's not needed for that to be stated because we know that Charles's Law, regardless, has constant pressure. So that's additional information we don't really need. My next tip is going to for you guys to always label your variables. So we know that we have volume and temperature 1, volume and temperature 2. What that represents is your initial and your final. So here's where all of our reading skills are going to come into play because we need to figure out which numbers are representing the initial values and which numbers are representing the final values. So we're going to be looking for keywords that kind of talk about the before and the after. So one more time by reading the question, we can see what is the temperature of a gas that is expanded from. The fact that they're saying the question states from, it's telling us that was our starting point. So our V1 is going to be 2.5. And we know then that the Celsius, right, because it was at the beginning, we're going to add 273. So when we do that, we get 298. That's the number we will actually use for our calculations, and that represents our T1. Now, the question says that it's going from 2.5 at 25 degrees Celsius to 4.1 liters. So because it has the word that is going from and to, then that 2, whatever's after that, that is representing the final. So this 4.7, that is going to be our V2. And the question is asking you, what is the temperature? So the question is asking you for T2. So now that we have all of our variables labeled, we just need to use our equation. And now what I'm going to do here is going to be just setting it up. So for V1, we stated that that was going to be 2.5. For temperature 1, it's going to be 298. Then our volume 2 is 4.1, and our temperature 2 is what we're looking for. So then at this point, you have a fraction that you can actually use cross multiplication, and honestly, that's the easiest thing. So what we will do here is going to be 4.1 times 298. That answer divided by 2.5. The same way you are taught in math classes to do cross multiplication, that's exactly what you're doing here. So when we have our answer, which is going to be T2, we can make a prediction actually. So we know that Charles's law is a direct relationship. So if the volume goes up, the temperature will go up. Temperature goes down, volume goes down, right? So here let's just look, and I'm going to do that in a different color. Our volume went up, right? From 2.5 to 4.1. So whatever our answer for temperature is, it needs to be higher than 298 degrees. And it's actually our answer here that I have is 488.72, and that would be in kelvins. So that is our final answer that we have. Let's look at another equation. And remember, the way we solved for T2 was by cross multiplication. Next example. We are told that a gas occupies 40 liters at negative 5.50 degrees Celsius. If the volume increases to 85.0 liters, how many degrees has the temperature increased? So they're not asking us for what is the new temperature. They're asking us for how much was the new temperature increased by, right? So it's important that we read these questions because we don't want to calculate from one thing, think that that's the answer, when in reality, the question is asking you to do an additional step. So again, don't forget, always change everything into kelvins. So all of your temperature should be kelvins. So when we add 273, so for this one, negative 5.5 plus 273 is going to give us a total of 267.5 degrees Kelvin. That's the temperature we're going to use. And specifically because the question says a gas occupies, then that's our initial. So that would be our T1. The volume is going to be V1. We are told that if that original 40 liters is increased to 85 liters, which is going to be now our V2, we are now looking for the temperature, how much was increased. So let's first figure out, well, what is the new temperature? Because then we can figure out how much was the increase. So let's do our V1, which is 40. Divide that by our temperature 1, which is 267.5. We're going to do V2, which is 85. And then we're going to divide that by temperature 2. So just like in our previous example, what we are going to do here is going to be cross multiplication. So we're going to do 85 times 267.5. That answer divided by 40. So we end up with an answer for temperature 2 as 568.44. And I'm rounding there. That would be in kelvins as well. And again, our direct relationship stands true. We have an increase in the volume, so we would expect an increase in the temperature. However, this is not our final answer, right? Because the question is asking you by how many degrees was the temperature increased? So this is a quick idea, right? I'm going to do it in a different color. We started with the temperature so I'm going to do temperature. The initial one was 267.5. The final one was 568.4. So all we have to do here is to take the difference. So I'm going to do 568.44 minus 267.5. And my answer for this question, because it's asking us for how many more degrees was it increased, came out to be 300.94 degrees Kelvin, is by how much our temperature was increased. So it's important that we read the questions. Now let's move on to Boyle's law. For Boyle's law, it's the one that has the inverse relationship. So as we increase the volume, right, we add the container, the size of the container that we have our particles in, we increase that. Well, if pressure is how many collisions are happening, but with which force, well, then that means that the more volume they have to spread out, the less they are going to be hitting the walls of the container. They're not going to be colliding as often. And of course, because we're assuming that the number of moles and the temperature stays the same, well, that is not affecting it. So this Boyle's law is going to be an inverse relationship. So here's where we have our equation. P1V1 equals to P2V2. So notice it's a little bit different than the one for Charles. And again, the easiest way to remember the gas laws is just to know that Boyle's law is the inverse one. So let's look at an example. We have a balloon is filled with 73 liters of air at 1.3 atmospheres for pressure. What pressure is needed to change the volume to 43 liters? So again, here we don't have to worry about Kelvin because, well, we don't have temperature, so there's nothing there that we need to take care of. And as we learned before, our pressure can be measured in different units. But as long as our units for pressure are the same for your initial and your final, your calculations should work out just fine. So, however, of course, the one that we tend to use is going to be atmospheres. So let's go ahead and do this calculation. First, let's label all of our variables. We are told that a balloon is filled, right? So that is going to be volume 1. And it's going to have a pressure of 1.3. So that's pressure 1. We are being asked, what does the pressure need to be changed to, right? So that P2. If we want the new volume to be 43 liters, so that's V2. So what we are going to do here is going to be, now that we have all of our variables labeled, we're going to put them in the equation. So we're going to have P1, which is 1.3, multiply that out by V1, which is 73, and then P2, which is exactly what we're looking for, right? That multiplied by V2, so that would be 43. And just like in algebra class, when you are looking for the missing variable, so solving for x, is the same thing that we're doing here. We want to simplify our values, and then we want to do the opposite on the equation to figure out and have the variable by itself. So we are going to simplify the left side here. So we're going to do 1.3 times 73, and that's going to give us 94.9. And then on the other side, we still have P2 43. Now, if I want to get P2 by itself, right, we're solving for x is the pressure. What you need to do is the opposite. So we're going to divide, right, because parentheses means multiplication, so we're doing the opposite. So when we divide 43 by 43, that gets canceled. But what we do to one side needs to be done to the other. So we're going to divide this side by 43. And before we multiply this out, we can make a prediction. We know that volume and pressure are inverse. So if in this scenario, our volume went down, it went from 73 down to 43, then we would expect, right, because Boyle's is inverse, we would expect the pressure to do the opposite. So if volume went down, right, if our volume went down, we would expect our pressure to go up. So let's see if it works out. So we're going to do 94.9 divided by 43. And that comes out to be a pressure of 2.21. And again, I'm rounding, and that is going to be in atmosphere, so ATM. So that is exactly as expected. We said our volume went down, so we would expect the pressure to go up. And the pressure went from 1.3 up to 2.21. Let's look at one more example for Boyle's law. The question states, a sample of air has a volume of 1.25 liters at 182 kilopascals. What is the pressure of the same sample of air if the volume changes to 2.25 liters, while the pressure is held constant? Again, it is not necessary for the problem to state that the temperature is staying constant. We know that, right? Every time we look at the gas laws, we only look at two of the variables. The rest stay constant. So I can actually eliminate that section of the question. Again, with our technique, we are going to label all of our variables, put them in the equation, and then solve for the missing variable. So this right here is volume 1. 182 kilopascals is going to be pressure 1. We are being asked what is going to be the new pressure. So again, we're being asked for P2. Will you always be asked for P2? No, not right. Not necessarily, because you could actually be asked for any of them. It's just the way those questions were stated. And we are told that the sample of air had a new volume of 2.25. So that's going to be our V2. So let's go ahead and set this up on the equation. We have volume 1, which is 1.25. That is being multiplied by the pressure, which is 182. We're going to have that equal to the second pressure, or the final pressure, but we don't know what it is. That's what the question's asking us for. And then we're going to multiply that by the new volume, so V2, 2.25. Just like in our previous example, we are looking for our missing variables, so we're solving for x. So we're going to simplify the left side of the equation. We're going to do 1.25 times 182. And that side of the equation comes out to be 227.5. I rewrite. And you don't have to rewrite. I just like rewriting things. So now that I have my pressure, my P2 times 2.25, I can do the opposite to get it by itself. What you do to one side, right? These cancel. You must do to the other. So when we divide for pressure 2, we're going to have 227.5 divided by 2.25. That is going to give us an answer of 101.11 repeating. And that is going to be in kilopascals. With the pressures, again, you don't really have to change your units, but it is important that you keep them constant. Just make sure that they're the same for your initial and your final. So let's just look at this number that we just calculated and just make sure that it works out. So again, Boyle's is inverse. So let's look at what happened to the volume. The volume went from 1.25 up. So volume went up, right? It increased from 1.25 to 2.25. So then based on the law of Boyle, right, we would expect the pressure to go down. And let's see if that holds true. We started at 182 kilopascals and we ended as the final with 101.11 repeating. So yes, it holds true. It is always just good practice to double check that you are doing indeed your work correctly, because you already know and you can start to predict the answers before you actually do the calculation. So that is it for this lesson. In our next lesson, we are going to look at the next two gas laws, which is going to be Gay-Lussac's law and Avogadro's law. And we will also include the information for Dalton's law of partial pressures, which is also important to learn. And then upcoming lessons are going to be on the combined gas law and the ideal gas law. Thank you guys so much for watching.